Number 4 on the problem set. What question do you have about number 4? Problem set. This is number 4. Okay, cool. I'm really confused on number 1. Okay. Oh, okay. Yeah, I can go through that again as well. And we can talk about number 1. Talk about anything you like. So in class today, the thing I was saying was that in a general aldol reaction, so let's say we ended up with this sort of product. In order to get this alcohol to eliminate, we first need to be able to completely deprotonate the compound before. So we need to have hydroxide. It'll take away this proton. And it'll go to an intermediate enolate. And from this intermediate enolate, this is able to then kick out the hydroxide. So this is the general reason why. So in the context of this problem, there are some cases where you can't eliminate the hydroxide at all because there isn't an actual hydrogen. So that would be like considering answer D, perhaps. So we can look at how answer D would form. So for any of these, for when you're trying to choose the correct product here, there's a number of factors. The main things that will come into play are potentially reversibility. So in the event that you cannot eliminate the OH, usually these are still reversible reactions. The ring size that forms, where 5 is usually favored over 7. And the general reactivity between aldehydes and ketones. So in this case, to get to this potential product D that isn't able to eliminate, we would first make our enolate by deprotonating aldehydes. Proton transfers like this are disfavored in the equilibrium, but you can still form them to react. So now we have an enolate. It's going to be nucleophilic at this carbon. So electrons will come down, and it can do an attack on this carbonyl. Since we're using this carbon to attack, we can number this as 1, 2, 3, 4, 5. So we know we're going to be making a 5-membered ring along the way. See, the aldehyde is still here. We end up making a fully substituted carbon 2. This at first is going to be an O- as an alkoxide. And it'll get reprotonated. Yeah, attacking, if I said something different, aldehydes are the most reactive and they will be attacked faster. You can make enolates of ketones and aldehydes pretty similarly, and it's which one will be attacked will be best. So yes, attacking an aldehyde is more favorable. I thought the ketone would go through resonance because aldehydes are more reactive. I am just drawing one possibility to show why this doesn't eliminate. We have not gotten to the right answer yet. So in this process, there's a lot of consideration. Since you asked about the alcohol not eliminating, I'm showing the example from earlier today a bit more explicitly to show how we got to alcohol D that was shown on the presentation, and the idea that now we don't have a hydrogen on this carbon that can be deprotonated. It's just an aldehyde and a methyl. So we need to be completely making a negative charge on this carbon to make this eliminate, or alternatively, fully make an anion here. But that pKa is ridiculously high because there aren't any places to stabilize. So as you mentioned before, attack on a ketone will be slow. We end up making a very sterically hindered bond along the way. So this is going to be unfavorable. And in fact, all of these steps end up being reversible because you could have hydroxide come back and deprotonate this alcohol again. This alkoxide could actually have its arrows go backwards. I'll make the arrow in a different color. You can actually have arrows that go down. Oops. Let me erase this so we're not confused. And then it would go back up to the aldehyde and would ring open again. So these are actually all in equilibrium. So frequently in these reactions, we want to find out first what is going to be the fastest, and then which one ends up getting stuck post-equilibrium stages. So whenever we have situations like this where we can't eliminate the alcohol, they can actually always uncyclize and essentially go back to the starting material where you try again. So let's take this and try to do something else. I'm going to just move this down so we can reference it. So let me number. So if we're looking to try to figure out, which way will this go, we want to probably consider still 5-membered ring attacks. So we have a couple different options. So our 5-membered rings that can form are starting from here, because we had it 1, 2, 3, 4, 5. And this means that if we try to use the other carbon from the ketone to attack, this would be a new 1. This would be 2, 3, 4, 5. So this would be an attack on an aldehyde. We'd expect that to be faster, so that seems pretty good. If you try to count the number of carbons to go from this methyl, it ends up being 7 carbons away from this methyl, so that's probably too far. So now we want to consider making the enolate from the ketone. Oh, my hand. Draw better. We have 1, 2, 3, 4, 5. Could always renumber this. And now we end up making a new equilibrium along the way. So this is where we want to be careful about where all these different groups are. Numbering, never a bad idea. So let's say this is going to be 1, 2, 3, 4, 5. We know that this aldehyde becomes an alcohol. So if this is going to be 5, we need to have the methyl right next to it. So this would be 5, 4, 3, 2, 1. It reforms a ketone afterwards. Now we do have this alpha hydrogen here, so we will be able to deprotonate the carbonyl, or the hydrogen next to the carbonyl. For the sake of rewriting a lot of structures, I'm going to show a proton transfer that moves this hydrogen to this oxygen. It would still be 2 steps overall. And I'll draw it in the enolate resonance structure. If it helps to draw them as the carb anion form, so if you wanted to instead draw this like this, I will be just fine with that. as long as you would be able to answer a question about what is the greatest, resonance isomer. It would actually be on the charge, but a lot of times drawing the charge on the carbon will help predict the reactivity a little better. And this can go down. And now we have an intramolecular elimination of hydroxide. This step ends up being less reversible. We end up with our alpha-beta unsaturated carbonyl compound. And we get to this structure. Note that I think you should probably go and check, but I think some of the answers that are listed on problem 4 aren't even possible cyclizations just due to the presence of where the methyls are. So this one has a methyl here versus there versus there. In reality, some of these would not even be feasible. Does that answer questions about number 4? Cool, yes. Yeah, so these require a bit of practice. They do usually have, or there will be competing cases where there will be one good answer, but sometimes you need to go and consider a couple options. And the more you practice some of these enolate attacks and consider different possibilities, it'll help to practice the intermolecular cases too. All right, there was someone who had a question about number 1. We're gonna go retrieve that. I'm gonna mark this page so that it ends up going up to the top. So this one's asking which one will create a racemic mixture when treated with base. So the first step to answering this question is, what is a racemic mixture? So remember what a racemic mixture is. Chirality, okay. A pair of enantiomers, that is very true, or a mixture of enantiomers. And so enantiomers are mirror images. Sophia, do 12, 10, D, and E involve the aldol reaction? I'll answer that later on, but given the section we're in, that is almost certainly a yes. But I'll answer that more formally. So we're talking about mixtures of enantiomers. So this is something just to kind of remind us. That means that if we had, say, methyl, ethyl, make that a hydrogen, and a butyl, these will be mirror images of each other. So when we look at these different compounds, first, the other element is we do need to have something to be chiral in order for it to create a racemic mixture. Things that are achiral would not be a racemic mixture. So are any of the options in 1 achiral, things that are not chiral at all, that we could just eliminate right now from the get-go? A has no stereocenters. I agree. Let's get rid of it. Are there any others we can get rid of? C. It has no stereocenters. It can't be a racemic mixture. Okay, so now we got it down to perhaps what the question is already implying. We have B, D, or B and D. So all of these have stereocenters that are shown. So they are chiral molecules starting out. So what happens whenever these molecules are treated with base? We've already seen this, right? We're going to be deprotonating next to the carbonyl. So would we be able to deprotonate this orange hydrogen? Is that a hydrogen we can deprotonate? We see a lot of no's. So will we be able to racemize, which means make a mixture, the orange hydrogen, or will it stay the exact same stereochemistry? Yeah, it's not alpha to the carbonyl, so it's going to stay the same. So that means if we had B react with base, we would end up making a mixture of these two compounds. I'm going to say phenyl to save time. And for D, we'd end up getting a mixture of these two compounds. So now we ask the question, is let's call this B and B prime, and this will be D and D prime. Why is there a difference in the hydrogen of B and D? Aren't they both the same stereochemistry? So I drew, this is these are both the original molecules, and these would be the new stereocenters that would form. Yeah, one was alpha to the carbonyl, one isn't. Yeah, so we never changed the orange hydrogen. The orange hydrogen stereocenter stays the same. So I'll mark these with a star. This one did not change, but the blue one can still be deprotonated because it's next. So the intermediate will be this enolate, and this is what ends up being flat. So when this gets reprotonated, it can come from either side. The methyl, though, it'll always stay relatively forward. Okay, cool. So yeah, so I guess now the question is, do you guys think that B and B prime is this represent a racemic mixture? And D and D prime, do these represent a racemic mixture? I think only D does. Why do you think? So what's wrong? What's wrong with B and B prime? Yeah, these are no longer mirror images. Does anyone know the name that describes the relationship between B and B prime? Yeah, so these would be diastereomers. I don't know if you guys learned it. If you only switch one center, it's actually called, it has a more specific name called an epimer. You don't need to know epimer. So the thing is, in order to make an enantiomer of B would have an inversion of both of the stereocenters. So it would be this molecule and this molecule. These would end up being mirror images of each other. If you wanted to be more explicit, we can use our little RS nomenclature. If you guys want to practice that. So this would have a priority of 1, 2, 3. So this would be an S stereocenter. This one gets switched to an R. And this would be a 1, 2, 3. This is R and stays R. So B is represented as RS stereocenters, where B prime is RR. When you only change one of the stereoisomers, they are diastereomers. In this case, we just have a single switch for the other one. If you change a single stereoisomer and the molecule only has one stereoisomer, the epimerization of them becomes racemic. Yeah, so this actually, the question is almost more to do with remembering what a racemic mixture versus a diastereomeric mixture is. I'm going back up the top. We did 4. We did 1. Or 6. I form enolate. I'm not sure when the double bond reforms and other things happen. 6 is the next question we'll discuss. All right. So this might actually, I think this comes up in lecture 29. But a lot of these types of reactions have a lot of similarities. So even if you haven't seen lecture 29, you might be able to start to get pretty close to these problems. So we have a few different things in here. So we have sodium ethoxide and ethanol. And then we have a non-enolizable methyl ester, and we have an enolizable methyl ester. Maya, I can answer that. The carbonyls to bromines, I would consider a two-step process that you already know from earlier sections. So I would think, what types of functional groups do you know? What turns into a bromine that you know well? And there's a functional group that we've used a lot that we can convert to a bromine. And then there's a way to turn a carbonyl into that functional group as well. Gotcha. So in this case, what do you think is going to happen first if we mix these 3 components together? Sodium ethoxide and these 2 esters. The ester will become an enolate. That's good. So this still has, oops, wrong pen. This still has alpha hydrogens that are acidic. They're less acidic than ketones, but we can still make our equilibria. So we're going to start equilibrating. And what is this enolate going to do? It'll attack the phenyl ester. I like that. So when we have a case where one's enolizable, one's not, we're going to assume that we're probably doing some engineering tricks to slowly add in the methyl, the enolizable ester, so that we only get the product we want. And this will follow the same idea. We have an even stronger nucleophile. This will attack an ester. I'm just going to say phenyl, so I don't keep drawing that out. So this is a tetrahedral intermediate that we have seen before in class. What happens to these types of tetrahedral intermediates? We have an O minus, a carbon, and then a methoxide. Boom. Boom, we're going to do the collapse. Yeah. So this will quickly kick out this leaving group. We make a new compound that looks like this. And what else can happen to this molecule? Or is this the end? Are we going to get here and we're going to be like, oh, there's B. We're going to call it a day. All right, so we have 2 things that I both like. Oh, that's a pretty good question. It has to do with the hybridization and some of the stabilizing energies. So this is something, yeah, I haven't thought about this type of thing in a while, but this is a good point. Usually collapses happen from tetrahedral intermediates, not trigonal planar intermediates. So the question I believe is, why doesn't this happen? And it really kind of comes down to there's some orbital reasons why. The molecule that would come out is called ketene, and this would react super fast right back in the other direction. Usually these types of collapses happen very quickly from tetrahedral centers, but not so much trigonal planar. I know this is not the most satisfying answer, but ketenes, in some ways, I think there's not an energetic benefit that it gains along the way. So one thing that could happen is, yes, enolization. The alpha hydrogen here now becomes way, way, way more acidic. So now we're in a pKa range of about 10. So this means that we're going to have a potential deprotonation. And we will have a deprotonation. That will get us here. So something else that happens, they mentioned that the methyl changes to an ethyl and the esterification. So this is something else you want to pay attention to. Usually you'll be trying to match the type of base you use to the type of ester. So if you had a methyl ester, you'd probably want to go in with sodium methoxide. If we're using ethanol as a solvent, yeah, pretty much. Transesterification is faster than a lot of these intermolecular reaction deprotonations because the equilibrium here is relatively small. We have a lot of base and a lot of the reagents, so transesterification is fast relative to these other reactions. And since we have a large excess of ethanol, this is what we're running the reaction in. We would assume the equilibrium for now transesterification will be favoring this general pathway. And under basic conditions, this is a two-step process. It probably doesn't happen on the enolate, actually. I'll draw it on. This would probably happen very early on in the reaction. So let me, just so I'm not misleading people, I'll draw this a bit over here. No. My pen. So early on in the reaction, we'd have ethoxide, and we'd make the ethyl ester. And this will be faster than, I think this is a Claisen, right? But let's just call it an aldol. They all are pretty much aldols of different types. There's not an aldehyde involved here, but we're still going to call it an aldol. And I'll write a note. Excess ethanol drives equilibrium. And so so at the end of the day, we won't have this methyl ester, right? We're going to end up having an ethyl ester here. And now we have a very stabilized enolate. And this will not be able to react again with another ester. This now becomes too uphill in energy, and it won't be able to attack again. It will happen with both of the esters. This will be the first thing that happens. I'll just draw this. I won't draw out the mechanism. The mechanism is the same. Yeah. So you won't be able to stop that from happening. So this enolate is very stable because we're able to have resonance structures that puts this charge on two different oxygens. We're actually going to do this. I'll move this just put it in a box. And it's this resonance delocalization that makes it stable. And it's going to be uphill now trying to attack an ester and break up its resonance. This will still be able to react with certain types of alkyl-halides. I think we go through that in, it can still attack aldehydes. It can still attack ketones intramolecularly. It can attack certain types of alkyl-halides. So it's still useful as a nucleophile, but it won't be able to react further in this case. Okie dokie. Let me keep going back up. So we have questions. Oh, do 10D and E involve the aldol? Oh, this is interesting. No, these do not involve or they don't have to involve. They shouldn't involve an aldol reaction. E actually you know how to do without any of this chemistry. E you could have done before learning anything in this section. It's just there to make sure that we can build molecules. Oh, I'm saying on E, you don't need to you can actually solve this without using reactions from this section. I will note that these they actually do require probably 2 or 3 steps. That is something that you could certainly consider for E, yes. Number 2, sorry, I need to get to number 2. I think that's the next one, right? Number 2. Which of the following is the most acidic? These are good thoughts for E. On number 2, I picked the answer with the most electron withdrawing groups. Well, which one do you think has the most electron withdrawing groups? I would agree that is a good start, but we may need a bit more analysis. To take us all the way home. E was the one I thought had the most electron withdrawing groups. So I would say that the double electron withdrawing groups will certainly help us out. So let's just get rid of B and D. But that brings up an interesting point. So a question I didn't ask, what is more acidic? B or D? Yeah, so D is more acidic. So I mentioned this a bit in class today. It has to do with the resonance stabilization of the ester. It largely correlates also to how esters react in general. Esters are less reactive to nucleophiles, and they're also less reactive to deprotonation, to bases. Sorry, my pen switched to eraser mode. So usually in these molecules, we have this resonance stabilization. That is always there. So whenever we go and deprotonate with a base, hydroxide's a poor choice here. It would actually just hydrolyze some sort of base. We lose the resonance of the oxygen. So this lone pair is no longer able to add into that electron deficient carbon. In a ketone, we don't have to overcome any other competing resonance stabilization. And it just becomes an enolate. So if ketones are more acidic than esters, does that change your thought on this problem at all? Yeah, so there's two different factors. Definitely you want to pick one of the molecules that has the most resonance. B and D are definitely not going to be the right answer. I was just bringing this up to talk about esters versus ketones. So this gets us down to quickly considering A, C, and E. They would each have, being able to put on the enolate side, on the product stability, they would both have put the negative charge on two different oxygens. The other thing we need to think about is, what does it take to actually deprotonate it in the first place? So these esters will lose some of the resonance stabilization after deprotonation because this won't have, that won't be present anymore. Yeah, so the one with two ketones would have the least to overcome overall. That would be the most acidic. So if you have two ketones, if you have a hydrogen surrounded by two ketones, it would be more acidic than one next to two esters, or one that's an ester and a ketone. Another way of looking at it is the reactivity of an ester enolate versus a normal enolate. In this case, we also have this oxygen that's sort of like an electron donating group into this double bond. So this further increases the nucleophilicity and the energy of that pi system. So this becomes a very, very electron-rich double bond, where this one is a less, where this is a less electron-rich double bond. Right on. Does anyone else have any other? Can we reason? Let's reason. Let's consider. Oh, so this actually coincides pretty well with what we were just talking about, right? How timely. So are there any that you would want to take off the table to begin with? Any initial reactions to any of these molecules? So we want to remove C. We're kicking C out of here. It's neutral, so that's usually a pretty good one. So we want to get rid of E. Why do we want to get rid of E? Or what is your rationale for B, E? Esters aren't reactive to nucleophiles. So this is in this case, we're saying that each of these molecules would be the nucleophile. And so since esters are harder to deprotonate, this will be more basic and more nucleophilic than a normal ketone. And it's because we know that it's the carbons that end up being nucleophiles when we deprotonate a carbonyl compound. And not only does this have electron donation from the oxygen that's deprotonated, it has added electron donation from the lone pairs on the methoxy too. Someone said B. So we said that we have a reason why B is going to be less nucleophilic than E. Where does D fall in all of this? Do we think D is going to be very nucleophilic relative to A and E? D, not nucleophilic. It has the most resonance. I agree. So D will be less nucleophilic than even B. We said that B was more nucleophilic than E. So now we're down to E and A. So I would say all of the compounds listed here are nucleophiles. If you drew any of these and asked me, is it an electrophile or nucleophile, I would say all of them are nucleophiles. I'm saying that its nucleophilicity, so like how reactive it is as a nucleophile, will be less than B or E because it does have resonance stabilization. So for a good nucleophile, you want to have sort of concentrated charge in a single place. If you can spread it down, all of those electrons go down in energy, and they want to go react as much. Yeah, so I like what I'm reading on here. So now we're comparing essentially something that has two oxygens versus something that has two nitrogens. And we know that N minus compounds are very reactive, very unstable. So that means that it does have delocalization. This would be the enolate of an imine, or actually an amidine. So this is not going to be nearly as stable as even something like E. It's actually even really difficult to make compounds like A because they really aren't the corresponding compound really is not very acidic at all. This would have a very high pKa. So this brings in a lot of the same sort of ideas of stability and reactivity. We would also say that A is the most basic. Let's revisit 6. Where are you, 6? Okay, so there's two things going on at once. So did you follow the transesterification? This was sort of a side conversation. Was this fairly clear? Okay, so this is going to happen first, and we're going to switch everything to ethyls. So I'm just going to go ahead and switch these to ethyls so that we don't have this happening again. Oops. And then I'll go address something that I said in class that is confusing maybe. These all have ethyls. So after transesterification, the next thing, the ending didn't make sense to you. Okay. So if you have sodium ethoxide around, I'll just do this. I'll just draw this out. So you add in methyl benzoate, you add in methyl acetate, and you put it into a solution of ethanol, and you add in some amount of sodium ethoxide. So any sort of time you have a solvent, we assume there is much, much more than reactants. So if you have, you could assume there's going to be more than 100-fold excess of ethanol around. So there's two things that ethoxide can do. It has the option of attacking one of the esters, and this will go to the tetrahedral intermediate. And this is transesterification that we learned in the last section. So these are all reversible. And as a byproduct, we're going to end up making methanol. First it'll be methoxide, and then it'll become methanol. So since this is going to be an equilibrium going back and forth, the side of the equilibrium that's favored is a side that essentially has more of the alcohol. So since we have a lot more ethanol than the amount of methanol we produce, that means that this whole process will be very much shifted in the forward direction. And essentially we're going to have only these ethyl esters as reactants early on. The same thing will happen with the phenyl ester. The same process, a little bit back, but mostly going forward. And you'll make the ethyl ester. So this will be the first stage. So then once these are all equilibrated, we have 99% ethyl esters. Now we have a situation where the base will probably start doing something else. Now we're going to have our ethoxide base start deprotonating these reactions, and it'll go through the process we had above. Does that help clarify the transesterification that happens initially and how we'd end up with all ethyl esters at the end? Okay, well, I hope that makes sense now. I'll keep moving on. Let's take a look at 8 real quick, and then we can go to 9. The second step. In lecture 28, the double bond is broken and the ethyl is added. But today you said the ethyl lithium attacks the carbonyl. In lecture 28, when did an ethyl attack a double bond? Was it a cuprate? Okay, so did that clear things up, I hope? Exactly, yeah. Both of those things happen simultaneously. actually transesterification would probably happen faster, and then you'd continue on and do the other chemistry. And even if you ended up making some of the other product first with the other reactions, the product could still do transesterification. Let's look at number 8 and 9. We'll do both of them. I ended up getting on here a little late. I'll give, if you guys want, I could stay on a little bit after. Oops. I don't remember where in 28 we have a double bond broken. If I'm covering 8 and 9 right now, I can maybe give you some verbal advice on 11. Oh, it's alkylation of esters. Okay, cool. Yeah. This will still, as I said in class, this is going to react. Different types of carbonyls. We're going to talk about 9. Okay, cool. So we have sodium hydroxide and we have 2 aldehydes. So this is an aldol reaction. We have 2 different aldehydes. What is one of the qualifying things we need when we have 2 different aldehydes to get it to work well? Does anyone remember? Yeah, non-enolizable. What happens if we have 2 aldehydes that are enolizable? A mixture is formed. I agree. So to sort of visualize this, we could have this attack this aldehyde. This could also attack this aldehyde. Or we could have this aldehyde attack, or it could attack this aldehyde. So you'd expect 4 different products. That one wasn't, there's no tricks here. Mechanism number 11. Was I getting spicy with mechanisms? Oh, I was getting spicy. This is great. Cool. This is one of my favorite problems. So how do you guys think? What can happen to this molecule? There are 3 different ways that methoxide can react with this starting material. Let's see if we can at least come up with the 3 to get you started on it. Bn, just for reference, is this. This is just a generic group. This is a benzyl. The hydrogen can be removed to make an enolate. Sounds like a possibility. So this is one thing that we can have in solution. Are there any other things that sodium ethoxide could do? Or what would you want to do with this enolate? Or do you think this is going to be a non-productive pathway? Yeah, so in the end, the reaction between something else will happen much faster than this enolate attacking another enolate molecule. Another thing to consider is this enolate is very hindered, and that's going to be a slow process. It also doesn't help you get to the product because the product isn't a combination or a dimerization where you bring two molecules together. Or are you saying that the methoxide could attack the ester? That I'm fine with. This is one of the possibilities we could entertain. But as you can see, this also doesn't really help us out at all. Because this would just break down and collapse, and we get the starting material back. I'm saying that these are all things that could happen, and we have identified two of the three that are non-productive. So we had methoxide act as a base. We just need to come up with one more reaction that it could do. Oh, sodium methoxide attacks ketone. Cool. Can this intermediate do anything? Can it ring open? How would it ring open? Which bond are you going to break? Yeah. So this is one of the more difficult things to see sometimes. That's why it's on the problem set. We can think about it. In this case, the methoxide is one potential leaving group, but that would just get you back going to starting material. An alternative way to break this is actually this carbon can be a good leaving group because we can put the charge onto the ester. So if you remember when we were talking, I was drawing on this. I don't want to do this. I wanted to do this. Let me go copy this over. Copy. I want to refer back to the note in it for a second. If we go back up to our earlier comments, from the very beginning, we saw very similar things with ketones, where when we have this O minus, such as this was able to be deprotonated and go backwards. This is a retroaldol, or in this case, actually this is a subset of the Claisen reaction. It would be called a retrodeacmin. But this, organic chemists, we just have too many names. And so I would ring open and then see how that can get to the product. So I'll leave you with on that note. So I would work on drawing out this product, seeing what else you can do with this intermediate, potentially different ways to cyclize again. Hope everyone has a good evening. I'll see you tomorrow night, perhaps. One more office hour. It's going to be great. Organic chemistry. So exciting.